Good morning, everyone. I'm Bingo from National University of Singapore, and I'm presenting our latest work on LLM serving, cost-efficient large language model serving for multi-turn conversations with CachedAttention. This is a joint work with Shanghai Jiaotong University and Huawei Cloud. So Transformer has been a successful architecture for generative applications. For transformer architecture, transformer model usually consists of several transformer layers, and each of layers is composed of self-attention and FFN modules. And the self-attention is the core mechanism of the transformer model. And in self-attention, it's use the intermediate data QKV to compute the attention score. And because the intermediate data K and V are usually reused across the generation, so K and V can be cached in GPU's HBM for during the whole generation. And the inference can be logically classified into two phases. The first phase is the prefilling phase. Prefilling phase processes multiple tokens in parallel to produce the K cache for multiple tokens. And the decoding phase processes single token sequentially. It means auto-regressively generate output token by token. And if we look at the two phases characteristic, for the prefilling phase, it's the execution time increase linearly as the input length increase. But for the decoding time, the execution time is relatively constant because for each iteration, it only processes a single token. And equipped with the transformer basics, we look at a common application, multi-turn conversations with LLM. So, for example, here is a LLM. Here is a travel. The user wants to ask travel suggestions from the LLM. It may ask several questions based on the answers from the LLM. And for LLM, it needs to read the chat histories of all the questions and answers to understand the context and then make the answer. So for the multi-turn conversations, we analyze the ShareGPT, a real data set from ChatGPT. So we can see more than 75% of conversations are multi-turn conversations. So multi-turn conversation is a very common application. And if we look further into multi-turn conversation, the multi conversation involves in many K cache computation. For example, for the second tense question, the LM not only need to process Q2, the new input from turn 2. The LM also need to compute Q1 and A2's promote because LM need to understand all of the context. But due to the limitation of LM, due to GPU's HBM, after serving the first round of first tense question, GPU need to discard the K cache because it needs space to serving other questions. So in the second tense question, GPU needs to recompute many tokens, recompute many K caches. So this is not efficient in multi-turn conversation inference. And we perform a study on the ShareGPT dataset. As we can see, as the conversation in the left figure, as the conversation tends continue, more than the almost most of the tokens for the prefilling is used for the prefilling is the history, is the chat history, and only a very few of tokens are used from the new input. And for the GPU time, we can see more than 99% of GPU time are paying for the recomputation. So our opportunity is save, load, and reuse KV cache by using off-GPU KV caching system. For KV cache saving, when the conversation is inactive, when the conversation is inactive, we can save the KV cache to off-GPU KV caching system. And when the conversation resumes active, we can load the saved KV cache from the off-GPU KV caching system. And by save and load the KV cache, we can reuse the KV cache from the chat histories. And so the prefilling cost is minimized because the LM only need to prefill the new input, and the recomputation cost is also reduced and minimal. But however, implementing such a KV caching system is not straightforward. We still have some challenges. The first challenge is the high KV cache access overheads due to the access to the KV caching system. For example, for the KV cache loading, when a new request hits the KV cache in the KV caching system, it needs to load KV cache from the caching system. So the loading time can create a gap between the last job and the current job. And also for the KV cache saving, after a request is finished, GPU need to save the KV cache from the last request to the KV caching system. So there will be a gap for writing the KV cache into the KV cache system. And secondly, the second challenge is the high storage capacity requirement of KV caching system. KV cache occupies a lot of storage. For example, for OPT 175B model, each token can occupy 4.5 megabytes, and for the 2,000 tokens, it can occupy 10 gigabytes storage. And for example, for 100 gigabytes memories, it can only store 10 KV cache items for the OPT 175B model. So a possible solution is to apply the cheap but large capacity SSDs to extend the KV caching system to allow more KV cache can be hit in the KV caching system. But if we use the large cheap storage medium to extend the storage, the placement of KV cache can be a problem because if we want to fully utilize the bandwidth between GPU and the host, it's better to place the KV cache in the host memory, in the pinned host memory. So we need to find a strategy to place the KV cache in the when the KV cache is hit, the KV cache is better to be placed in host memory. And the fourth challenge is the unexpected invalidation of the saved KV caches. So for the LM inference, the chat history may exit the context window of the LLM. So LLM need to truncate the promote to make the promote fit to the context window. So if we save the query cache from the for the promote at before the truncation, but the query cache actually is embedded with the positional information. So after the truncation of the promote, for example, here the middle tokens are 2,000. The position is 2,000, but after the truncation, this token can be 0 position. So the query cache, the embedded position information is out of date. So we need to recompute the query cache when the context window overflow. And this will result in many recomputation costs. So we propose the CachedAttention to solve these challenges. And I will detail this the technique we used to tackle these challenges. So to solve the first challenge, we use the overlap query cache access technique. So we can use layer-wise execution property to reduce the gap of loading and saving query cache. For example, for query cache loading, we can while computing the layer 1, we can load the query cache of the next layer 2 into the GPU. And by doing this, most of the query cache loading and the computation can be overlapped, but there will still be a small gap. So to fill this gap, we can use a small HBM buffer to prefetch the query cache. For example, during the execution of the last job, we can prefetch the query cache to the small buffer, and when the last job is finished, and the next job can directly start the computation because the query cache of layer 1 is still there, already there. So by doing this, we can fill the gap of the query cache loading. And similarly, we have the gap in saving the query cache. So when saving the query cache, after serving a request, we need to save the query cache from the HBM to the query caching system, and there will be this gap, and we can distribute this write to be overlapped with computation. For example, for when computing the layer 2, we can write the query cache produced by layer 1 into the query caching system, and so on. We can make the query cache writing and the computation overlapped, and then the gap can be reduced. And the second challenge, we use the second and third challenge. We use the large chip SSDs to extend the query caching system's capacity to make more query cache can be cached in the query caching system, and improve the system efficiency. But we want to make the query cache found in the host pin memory. So we design a scheduler-aware query cache placement strategy to achieve this goal. For example, when the LLM is processing job 1, we can look at the job information from the in the job queue, and in the job queue we find that job 2 is the next job, and the query cache of job 2 is already in the DRAM. So this is the best placement. And then we look at the next job. For job 3, its query cache is in the disk. So we need to fetch the KV cache string to the DRAM. First, the KV cache string can be swapped into the swap buffer, but we need to maintain such a swap buffer to make the algorithm work. So we need to swap the other KV cache from the DRAM to the disk. So here we can because the KV4 is the next job and it's not in the prefetching window, so we swap the KV cache of job 4 into the disk. However, disk is full, so we need to pick up some KV cache to evict from the KV caching system. Job 10 is not in the job queue, so we decide to remove the KV10 from the KV caching system. And by doing this, we can ensure that when job 2 and job 3 have an opportunity to be executed, its KV cache can be in the DRAM, and it can utilize good host-to-device bandwidth. And for the fourth challenge, when the context overflow happens, the KV cache in the KV caching system is becoming invalidated. So we design this decoupled KV cache truncation mechanism to maintain the validation of the KV cache. So for the KV cache truncation workflow, in the first step, when we save the KV cache to the KV caching system, we save the key and v value of that not integrate with positional information. And when the KV cache is hit, and when we want to fetch the KV cache, also when the context overflow happen, we can directly trunk the KV cache in the memory, and we can when we want to use the KV cache for inference, we can fetch the trunked KV cache from the DRAM to HBM, and then after that we embed the positional information, the new positional information to the KV cache, and then we can use this KV cache for inference. And by doing this, we can decouple the positional information from the KV cache, and the KV cache can always be valid. So for the we do extensive environment to verify the effectiveness of CachedAttention. So first, for the end-to-end performance, we first look at the hit rate of the KV caching system. And we can say by extending the KV cache system with large capacity SSDs, the hit rate is very high in our experiment. And with such high hit rate, we can achieve good TTFT, the time to first token. And it achieves up to 86 savings of TTFT. And because for the same amount of tokens, CachedAttention can use less time to finish the prefilling phase. So the prefilling throughput achieve 7.8 speed up by CachedAttention. And for the GPU execution time, because the CachedAttention can significantly reduce the TTFT, reduce the prefilling time. So here the prefilling time is reduced. And also because we reduce the prefilling time, and the interference of prefilling time on the decoding time are also reduced. So the decoding time are also reduced in our experiment. So and also For the context overflow, when the context overflow happens, the query cache become invalidated, and here is some overflow cost. And the query cache can also reduce this overflow cost. And we also evaluate is the total inference cost of CachedAttention. And as we can see, because we in CachedAttention can use less GPU time to finish the job, and it has less cost. And because we use some accelerate storage for storing the query cache, so we also evaluate the storage cost. The storage cost is minimal. It only occupies 9% to 16% cost of the whole inference. So in conclusion, we use multi-hierarchy storage to store query caches rather than directly discarding the query cache after serving a request. And by doing this, we can avoid recomputation cost of happen in multi-turn conversation inference. And this work has been announced as part of the service Elastic Memory Service (EMS) in Huawei Cloud. So welcome your attention, and thank you.